In this unit, we begin a discussion of chemistry in our overall topic of molecular biology. So, in chemistry, you probably last year didn't talk about where all the atoms originally came from in the universe, but and that's what we're going to do here in biology. The origin of life, from where did all these chemicals that we have in our bodies originate? Well, if you go way back, all the chemicals in our bodies have carbon atoms, hydrogen atoms, oxygen atoms, nitrogen atoms, lithium atoms, sodium atoms, chlorine atoms. Where'd all those come from? The universe is actually made up mostly of hydrogen and helium, and the Earth is kind of an exception to that. The Earth is full of all kinds of stuff besides hydrogen and helium. I mean, we have some helium, but not a lot, and we have hydrogen, but the hydrogen's actually locked up in water. So we have a lot of hydrogen atoms. They're parts of water molecules in our oceans and freshwater lakes, rivers, and streams. But we're not just a giant ball of hydrogen. We have like all kinds of goofy atoms in the crust of the Earth, from iron all the way to silicon. So we think around 5 billion years ago, a previous star that lived or existed in this part of the universe experienced a supernova explosion. And this is what a supernova explosion looks like through this, as taken through the Hubble Space Telescope. Now, in the cataclysm of this explosion, the hydrogen atoms that probably were in this original star smashed into each other at high rates of speed. And when they did that, they formed atoms that were bigger than hydrogen atoms. Hydrogen atoms that consist of only one proton. But when you slam multiple hydrogen atoms together, you get other kinds of atoms. And we think the Earth was formed from an exploding star that made a vast array of atoms from lithium to gold. Large clusters of atoms that stuck together ended up becoming planets and moons. And our sun had enough, oddly, hydrogen to begin a nuclear fusion event. And so the sun has been generating all of our light and heat, and that is what is running your body right now, is the fusion energy coming from hydrogen fusion on the sun. Hydrogen is fusing with other hydrogen to form helium atoms, and that releases an awful lot of heat and light. So we think this all happened around 5 billion years ago, and around 4.5 billion years ago, we think Earth collected from random dust in our particular space in the solar system. Now, when you form a bunch of random atoms, as we found out from like nuclear warheads, most of the atoms are not lucky in that they don't have the right numbers of protons with neutrons, and as a result, they're radioactive. And we think the Earth was highly radioactive, and that's probably why the core of the Earth is so hot. It's radioactive heat that's been trapped in the core of the Earth for the last 4.5 billion years. Now, at some point after the Earth was formed, the planet generated life. Now, we don't know exactly how, but it did. So here's our solar system. Here's Mercury close to the sun. Here we are. This is Earth flying around in its orbit. Here's all the bigger planets as you move out away from Earth. How did our little planet generate life, and none of these other planets generated life? Well, the first theory on this was produced by a guy named Alexander Oparin back in the 1920s. He was a Russian scientist, and he speculated that life began shortly after the Earth was created, maybe 3.5 billion years ago. We think maybe more than that now. He proposed that the early Earth's atmosphere had no oxygen gas. Instead, it was a reducing atmosphere. Reducing atmospheres are opposite of oxidizing atmosphere, which is what we have today. Reducing atmosphere have hydrogen gas, nitrogen, methane, water, and ammonia. His theory proposed that monomers, like simple carbohydrates, simple amino acids and things, formed in the atmosphere as a result of the interaction of these reducing gases. In the 1950s, Stanley Miller and Harold Urey thoroughly tested Oparin's theory by building a spark chamber that contained only reducing gases. After a week of sparking the chamber with electricity, their chamber produced all kinds of goofy organic molecules, proving that you could generate organic molecules from simply the interaction of electricity and reducing gases. So one possible origin of life would have been that monomers were created in the atmosphere from the interaction of reducing gases and lightning or ultraviolet light, and then the monomers would have rained down as pollution and accumulated in puddles. The puddles experience, drying and re-wetting, and that would have caused the pollutants, the little monomers, to polymerize. And when you get polymers wet, they tend to form cell-like structures. And the theory would have been that these cell-like structures forming in these pools may have led to the first cells. No one knows if this is true or not, but various other renditions of that theory have been proposed in the last 30 to 40 years. What we do know is that the spontaneous generation concept, which was the old theory that simple life forms could grow from non-living material, was incorrect. And if you remember from the introduction, I told you that Louis Pasteur, using the curved neck flasks, disproved the whole concept of spontaneous generation. So we don't think that is how Earth generated life. Now, what are atoms? Now, you learned about this last year. An atom is a tiny little particle of matter that has the properties of an element, like a carbon, silicon, lithium, sodium, hydrogen, oxygen, nitrogen, and so on. Atoms are made up of smaller particles, but they don't have the properties of elements. Protons, neutrons, and electrons make up atoms. The protons have a positive charge, neutrons have no charge, and electrons have a negative charge. As it turns out, the protons and neutrons are all packed densely in an area we call the nucleus, and oddly, without taking up almost any space, they have 99.9% of the mass of an atom. The electrons, which have almost no mass, occupy the most space by moving around. Don't think that these subatomic particles are not important. It turns out that your body runs on protons and electrons. You separate protons from electrons, and that's what's generating the body heat that right now you feel in your arms and your legs and your fingers. So electrons, if you remember from last year, exist in orbitals, and electrons like to move around among different atoms, forming bonds between different atoms. We don't need to go into the details, but atomic number is the number of protons that is in an atom, and that's a really important quality of an atom. The atomic number is what makes an atom an atom. So nitrogen has an atomic number of 7, meaning it has 7 protons. Carbon has an atomic number of 6, which means it has 6 protons. The two atoms have very different properties because of the numbers of protons that they have in the nucleus of their atoms. So what an element is a material that is made of only one type of atom. Elements are not really common on Earth. If you are digging in the ground and you find a diamond, a pure chunk of carbon, you've really got a lot of money in your hand because they're very rare. There's a spelling error I'll have to fix. Gold is another one of those atoms. If you find digging in the ground a chunk of pure gold, you've really got a lot of money in your hand because pure gold is hard to come by. The Earth is generally all mixed up, but not always. Now, there's 109 different types of atoms found in the Earth, in the air, and in the water, and in the crust, but only a few types of atoms are commonly found in living things. The most common atoms are carbon, hydrogen, oxygen, nitrogen, and phosphorus. Some of the less common ones are iron, sodium, chlorine, calcium, and potassium. They're less common, but they're ultimately extremely important. We won't talk too much about isotopes, but each atom has different flavors. There are different types of carbon atoms, and we call those isotopes, and they differ by their neutron number. As it turns out, most atoms have a perfect neutron number. That atom is not radioactive. Most of the other types of isotopes of the atom have imperfect neutron numbers, and they're radioactive as a result. And what they tend to do is kick neutrons out or kick protons out to try to get a stable ratio of protons to neutrons. But in doing that, they're releasing radiation, which is actually dangerous to you. So you don't want those things around. Isotopes are sometimes very valuable for tracing where atoms go in bodies. So they get used sometimes, especially in medicine, but we won't talk about them much here. Chemical compounds are different than elements. A compound is made up of the chemical combination of two or more elements. They're not just floating around each other, they're actually stuck to each other. One example is water, which is a combination of hydrogen gas and oxygen gas. They're no longer gases. At room temp, they're liquid because the hydrogen atoms are chemically bonded to the oxygen. So unlike elements, compounds are very common on Earth, whereas elements are very rare. Now, it turns out atoms like to stick to each other. We call this bonding. And in biology, there's three kinds of bonds you need to be aware of. Ionic bonds are where one atom steals electrons from another atom, and as a result, the two atoms have opposite charge, and then they're stuck together forever because of the opposite charge. For example, sodium has an unlucky number of electrons, so when it comes into contact with fluorine, which also has an unlucky number of electrons, fluorine steals this extra electron from sodium. That gives fluorine a perfect number of electrons in its outer shell. Sodium has a perfect number. Both atoms are happy, but because they are oppositely charged, they're stuck together. When atoms do this, they form crystals. This is an ionic crystal. What you have are little positive ions surrounded by larger negative ions in an alternating matrix. That's the way all salts are. That's called an ionic bond. There's a different kind of bond which makes up also in the human body, and it's really kind of more important. It's the covalent bond. In covalent bonds, atoms share electrons. So in this case, we have a hydrogen atom that has an unlucky number of electrons. When it comes up to another hydrogen atom, which also has an unlucky number of electrons, they each share the other's electron. That gives them each a lucky number of electrons, which makes them both happy, and so they form a molecule known as hydrogen gas. Carbon likes to do this. If you find a chunk of pure carbon from the base of a volcano, say, what diamond is, and that's what you've got in your hand, is carbon atoms completely surrounded by other carbon atoms, all intertwined with each other by covalent bonds. Those are rare. That only happens when carbon, in the form of usually graphite, is exposed to extreme heat and pressure, which is what you'd find around the edge of a volcano. At that point, the carbon atoms, instead of forming sheets, bond three-dimensionally and form a 3D structure. And that is what diamond is. So covalent bonds hold atoms together because of electrons that are being shared. There's no opposite charges. It's just a bridge between the two atoms where the electrons from one atom are actually shooting through a bridge and going around the other atom. Ionic bonds, remember, are attraction because of opposite charges, because one atom stole an electron from another atom. So in a covalent bond, there's no stealing, there's sharing. In an ionic bond, there's stealing. All right, now the last kind of bond we got to talk about is hydrogen bonds. Hydrogen bonds are about only 1 or a little more % as strong as a covalent bond, but they're very significant. They are the basis of all of the best glues, especially paper glues. Hydrogen bonds are what we call weak bonds because they're not nearly as strong as a covalent bond. And what they are is they are a bond between an oxygen or a nitrogen and a fluorine of one molecule and the hydrogen of another molecule, which is itself attached to an oxygen, a nitrogen, or a fluorine. Now that's a mouthful, but what we're trying to say is when you have oxygen, here in this case it's water, attached to hydrogen, you have an imbalance of electron sharing. As a result, this oxygen, this red oxygen ball, has a slight negative charge. And this little hydrogen ball here, because it's stuck to an oxygen in its molecule, it has a slight charge also. But the hydrogen is positive and this oxygen is negative. And that causes these two things to stick together. That is what creates water droplets on glass. Gasoline does not form water droplets on glass because it cannot hydrogen bond with itself. Water molecules can, and they form droplets. We'll talk more about this in a few minutes. But hydrogen bonding is what literally is cementing your body together. It gives your bone the strength it has, tendons and ligaments. are being held right now by hydrogen bonds, not by covalent bonds. Your body is not one giant covalently bonded molecule. You are a bunch of molecules that are stuck to each other, mostly by hydrogen bonds. Now, this is a fourth type of bond. I'm not going to mention much about these, but they're called van der Waals forces. You may have learned about these last year. That is what causes the gecko toe pads to stick to glass. Van der Waals forces are weak forces between hydrocarbons, essentially, in molecules. And it's what makes wax molecules stick together or oil molecules stick together in butter or margarine or earwax. We won't say much about these because they're not as significant to our discussion, especially an introductory discussion of molecular bio, but they do exist and they are significant in some way, shape, and form. So that finishes our brief discussion of chemistry, and next we're going to move on to a discussion of water.